Hello and welcome back to Calculus 1. We are continuing exploring chapter 3. We are going to talk about derivatives of trigonometric functions. And this is going to give us more insight also into product and quotient rule as we deal with trig identities and other things. So let's take a look first at basics. Good morning. The limit definition provide us for the derivative, provide us with a way to find the derivative of basic two trig functions, which are sine and cosine. But in order to do that, we have to memorize two limits that appear in the proof. And I say memorize because those limits are explained and done all the way in chapter 4 when we do Untitled Rule. So it's a little bit, it's interesting which way this works, where you guys, you know, it's all over the place to actually do the initial proof. But we start by memorizing that the limit as x goes to 0 of sine x over x is equal to 1. And we are also memorizing that the limit of cosine x minus x over, minus 1 over x is equal to 0 as x goes to 0. So these are the two limits that we memorize, and again we showed the way to calculate these limits in chapter 4. So once you have this, then you can go and write your limit h goes to 0 of sine x plus h minus sine x divided by h. So this is just a standard definition, and then when you when you expand the sign over here on the first one, you have limit h goes to 0. You expand the sign using the formula sine x cosine h plus cosine x sine h, and you have minus sine x, everything divided by h. So when you use the formula for sum of angles in a sine, you get the expansion, and then you take the first term and the last term and you factor out sine h. So you have limit h goes to 0, and in the first term you have sine x and then cosine h minus 1 divided by h, and then you have plus, you can split off limits using the rule, h goes to 0 of cosine x sine h over h. So when you do this over here, the limit operates on h as a variable, so x is a constant in the eyes of the limit because the variable for the limit is h. So you can kick sine x in front and have limit h goes to 0 of cosine h minus 1 over h. And you can do the same thing for the second one, where you kick out cosine x because again the limit operates on h only. So it behaves like a constant, right? So now this limit over here was defined as 0, and this limit over here was defined as 1 on top. So you see that what you actually get now is sine x times 0 plus cosine x times 1, and you get cosine x. So what we got from this calculation is that the derivative of sine x is cosine x. And that's the formula which we memorize. If you don't, well, you have the alternative to get it every time when it pops up, right? So you pick your poison. You're going to memorize this or do this every time you need it. It's your choice. I would never force any one of these on you, right? So this is the derivative of sine x. Derivative of sine x is cosine x. And then you can do the same calculation to find that the derivative of cosine x is negative sine x. And this would be the basic two, right? The first two out of 6 trigonometric functions. Can you give me another trigonometric function? Tangent. Good. Now, what would be the tangent, derivative of the tangent? How would we find that one? Should we use the limit definition, or we can use something more cunning? Yes? Not derivative of sine over derivative of cosine. Yes, derivative of sine over cosine. So if I want to compute the derivative of tangent x, I will rewrite that as sine x over cosine x, and then use what? Quotient rule. So you have derivatives of sine and cosine. Let me see. What do you get? Do it for a little while. Alright, so we know it's a quotient rule. Therefore, we take the denominator, square it, then copy denominator times the derivative of the numerator, which is derivative of sine is cosine x, very good, minus, then copy the top, which is sine x, and derivative of cosine is negative sine. So now we have cosine times cosine is cosine squared x, and then negative sine times negative sine is positive sine squared x over cosine squared x. So now what? What now? Yes. So 1 over cosine squared x, which is 1 over cosine is secant squared x. It's a formula. The derivative of tangent x is secant squared x. Perfect. Perfect, perfect, perfect. So since this was so much fun, what is the derivative of cosecant x? What are you supposed to write for cosecant? 1 over? 1 over sine, good. So we do the quotient rule again. We have sine squared x in denominator. Copy sine x, the derivative of 1 is 0, minus, copy 1, and then we have sine x, right? Sorry, the derivative of sine is cosine. There we go. The first term dies, and we have negative cosine x divided by sine squared x. Now that can be broken down into negative 1 over sine x and then cosine x over sine x. So what do we have? What is 1 over sine x? Very good. And what is the cosine over sine? Excellent. There it is. So let's write all 6 in one spot and see the cool ways of remembering all of this stuff. So we have the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. We have the derivative of tangent x to be secant x, secant squared x, and the derivative of cotangent x to be negative cosecant squared x. And we have the derivative of secant x to be secant x tangent x, and we have the derivative of cosecant x to be negative cosecant x cotangent x. All 6 on one spot. Do you notice any kind of patterns? Aha! Starting with a co is negative. Good. Cosine, cotangent, cosecant. So all the co ones are negative. What else? I guess hello and welcome back to Calculus 1. This is the second part of well, starting the part 2 of the trig. So we're talking about symmetries and ways to remember these trig derivatives. So you guys already noticed that if is one of the co-functions like a cosine, cosecant, and cotangent, they're all negative. Now I'm calling your attention to the trig pairing. Sine is always with cosine, secant is always with tangent, and cosecant is always with cotangent. Now also look across. You see the derivative of sine is cosine, the derivative of cosine is negative sine. Now look at the tangent x and cotangent x. You see the secant squared and negative cosecant squared? And then look up down, secant, tangent, cosecant, cotangent, right? Now those are also, I'm going to write this tangent nicer over here, but those are also lined up nicely for some kind of symmetry. So it's pairing. You will never find a derivative that mixes sine with the cotangent, right? So sine and cosine, tangent, secant, and then cotangent, cosecant. And then sine, cosine, cosine, sine, tangent, secant squared, cotangent, cosecant squared. Now it's cos, so it's minus. And then you have secant, which is secant tangent, and then cosecant, cosecant, cotangent with the co. Again, it's a minus. And that's it. I hope you're not disappointed. Now, there are two subtleties that we could discuss, but we actually don't have to, because we are going to deal with the chain rule today. So, right, 2 lectures away, 3.7. Oh, and then we have 3.8, 3.9, I think like 3.11. And that's it for chapter 3. So this is already halfway through chapter 3. So yeah, it's going to be another vote coming up. One of the things that the book obviously mentions is the fact that you can use that A, just like you used A for ease. So if you have sine AX, the derivative, right? If you have this, then the answer to that would be A cosine AX. So what's the derivative of sine 3x? It's going to be 3 cosine 3x. So this is something that we are going to address with the chain rule, so it's not as important as it was last time to learn the e to the ax, so you can do the homework that was not there, clearly, right? So now you have the same situation happen here. So this a goes in front, but we are going to take care of that later. And then the second subtlety that we have to address, again, is going to be the products and quotients and all that stuff. So what is the derivative of x squared cosine x? Right. That's something that we absolutely have to answer. So this is what? Product rule, good. So copy the first times derivative of the second times, plus copy the second times derivative of the first. The only thing we can kick out is x. I'm going to write the first term first because of the plus. Second one has the minus. So I kicked x out, so that's going to be 2 cosine x minus x sine x. And that's the factored form for the answer. You can only kick one x out and be done, no coughing. Bueno? So the rule goes the same, it's just, all right. Next question. What is the derivative of tangent x times cosecant x? Tangent times cosecant x. You want your exam? Definitely not Fernando or Matthew. Everyone done? All right, let's take a look. So it's the derivative of sine x over cosine x times 1 over sine x, then sines cancel, and then we have the derivative of secant x, which is secant x tangent x. Good. Right? Right. Good. Okay. What is the derivative of tangent 5x? It has to be 5 secant squared 5x by that rule that where you kick a outside. And that's it. We can do an awesome problem actually. We should do the problem per section every time. Find the equation of the tangent line for f of x equals 3 sine x over 2 at x equals pi over 3. So the procedure for the tangent line is a known procedure, and it is going to be in every section because you have the 3 parts, right? For tangent line, you are supposed to find the derivative so that you can get m. You are supposed to compute f of x so that you can get y. And then once you have m, x, and the y, you can use y equal mx plus b or the other one to come up with the line. So you just need all of the little pieces to fit together. You will calculate the slope from the derivative. You will calculate, so all of these parts. Everyone get their attention? Which one do you want? 5. I like 5. Which one is yours? John. One class practice, like when the student says, but I really think I need 2 more points on my test. Really? That's going to make a difference at 10%, at 2 points on the test? Yeah, but every point counts. No, it doesn't. Insignificant. In every aspect of that. All right, so we need the derivative first. The derivative would be, copy the constant. The derivative of sine is cosine of x over 2, and then that a is 1/2 goes in front. So the total derivative over here is 3/2 cosine of x over 2. Slope m is the derivative computed at the point which is pi over 3. So we have 3/2 cosine of pi over 3 divided by 2. So that's 3/2 cosine pi over 6. Cosine of pi over 6 is what? Very good. So 3√3 over 4 altogether when you compute. So you have your slope. The next is to find the y value of the function, because we need that as well to compute the line. We have to have a whole point. We only have x coordinate. So to find y, we will plug x in the original function, which is 3 sine, in this case 1/2 of pi over 3, which is 3 sine of pi over 6. Sine of pi over 6 is 1/2, so this is 3/2. So what do I have? I have slope that it's 3√3 over 4, and I have a point which is pi over 3 comma 3/2. Now you can use either y minus y1 equals mx minus x1, or you can use y equals mx plus b, whatever. Y equal mx plus b. Y is 3/2. M is 3√3 over 4 times x, which is pi over 3, plus b. The 3's cancel, and I multiply everywhere. I don't have to multiply by 4. I have b already. So b is equal to 3/2 minus √3 pi over 4. Now, to get the common denominator 4, you just need to multiply this, so it's 6 minus √3 pi. So what is the equation of the tangent line? Y equals 3√3 over 4x plus 6 minus √3 pi over 4. That's the equation of the tangent line. Your m and your b. That's what you have to find, m and b, and plug them into the equation. So every single section of chapter 3 has this tangent line problem. The only difference between these tangent line problems is this line here. What is the method to take the derivative? Is it basic derivative? 3.3. Is it product rule or quotient rule? 3.4. Is it trig? 3.5. Is it going to be chain rule from 3.7? Implicit differentiation, 3.8. Inverse trig function, right? So what from whatever, 3 point something. Logarithmic differentiation, right? So there's all these different ways to take derivative, and in the entire tangent line problem, that's the only line that changes from section to section. The rest of the procedure is the same. Plug in a point in a derivative to find the slope, plug in a point into the original function to find y, use m, x, and y to find b. So the tangent line procedure, and the tangent line is also the most important problem of Calculus 1, because tangent line measures the change, and that's what we are learning in Calc 1, how to measure the change using derivatives. Calc 1 chapter 5 and Calc 2 chapter 6 and 7 are teaching about integration, and that concept is a concept of accumulation. So technically Calc 1 focuses on the change and derivatives. Therefore, tangent line is the central problem. And obviously, every exam starting, so exam 2, exam 3, and the final exam must have a problem that says compute the tangent line, find the tangent line. Otherwise, exams would be garbage, because they do not address the central problem of Calculus 1. So this type of a problem, whether you take the derivative with the product rule or stuff you haven't seen yet, the problem of the tangent line must be present on every single exam. It's the central problem of Calc 1. So that's the tangent line. I think we did another tangent line at the end of 3.3. Find the equation of the tangent line, and there it is. We had 26x minus 71 as the answer. So we did that, and I am really planning on and hoping to do the tangent line at every single problem throughout chapter 3 as an example at the end. That's that. All right, next lecture. I have microphones, so I have to improvise. Yeah. Finally, those long-awaited rates of change, right? It's break. The door is right here. Firefighters, the windows are right there. And ninjas. We got it.